Now, let's continue. I will give the proof ideas of theorem 1. Let's recall the theorem 1. Theorem 1 is uniqueness theorems. Type 2, stable stationary emerged hypersurface in a ball in space forms must be total geodesic. Now, we denote the Jacobi operator J in this way. Thus, the stability of type 2 hypersurface and the rotating area fixed equal to the phi inequality for any phi satisfying this condition 6. This condition means the wetting area fixed. And the proof ideas is to find the appropriate test function with constricted 6 and put them into the stability condition phi. And now the question is how to find such good test function. For Euclidean space, R power n plus 1, because M is type 2 hypersurface, so M is minimal, we have the Laplacian, the product of x, A equals 0. Here the x is position vector field, and A is constant vector field in Euclidean space. And we can take integration by paths. We have 0 equals to this function. Now we replace the conormal of boundary M in M by the relationship A bar equals to mu sin theta minus mu cosine theta. We have the product of mu A equals to this equation from boundary M lying on the unit sphere. So we know the A bar equals to x. So this function not only defined on boundary M, but also defined on M. So we can take this function as the stability conditions text function. We take this function as a test function, and this satisfies the following 3 properties. And put phi A into stability condition, we can imply for each A from R power n plus 1, we have this equality. Here A is constant vector field in Euclidean space. And with summation, A equals to EI, here EI, here I equals to 1 to n plus 1. We can imply this equality. In particular, if the theta is a right angle, that means the cosine theta equals 0. So we have the normal of the H is 0. That means M is total geodesic. If theta is constant, is not right angle, then we consider the following auxiliary function phi defined in this one. And here the x is position vector field, and v and mu is the outward uninormal vector field of M. And phi satisfies Laplace phi equals to this function, and we can take integral paths by the Laplacian phi square. We have the 8 equation. Now we add 7 and 8. We can imply this equality holds. So we can imply the gradient phi equals 0. That means phi is constant. So Laplace phi equals 0. That means this equation, this function equals 0. So from this function and this function, we can imply the square of H equals 0. That means the M is total geodesic. Now we consider the parabolic space and the unit sphere case. Let BH be a ball in hyperbolic space with the reading R, and BS be a ball in a half unit sphere with the reading R. And we denote YA a smooth vector field in hyperbolic space and the unit sphere by the following way, YA. And we can easily to check that YA is Killing vector field in hyperbolic space and unit sphere. That is the following equation holds. Since that the M is minimal, so we have the divergence of the tangent part of the YA equals to 0, because YA is Killing vector field and M is minimal, so H is 0. So we can take integrated path. We have this one equals to 0. Now we can replace the mu, the conormal mu, by the relationship this, and we have the product of YA mu equals to this function. And we can choose the test function phi A in hyperbolic space and phi A in unit sphere. So we can follow the argument of the Euclidean space case, can prove that M is a total geodesic n ball in hyperbolic space and the unit sphere. So the theorem 1 is finished. Now we prove the theorem 2. Let M hat be a compact closed Riemann surface obtained from M by growing a conformal disk at any connected component of boundary M. Then there exists a non-trivial conformal map for psi hat such that the degree of psi hat is smaller than 1 plus G plus 1 over 2. And here G is a genius of M hat. And this is a take integer. Let phi be the restriction of psi hat to M. Then the psi restrict boundary M be a conformal emergent. By Hatcher and the other result, we can assume the integration of psi I over boundary M equals 0, and the I equals to 1, 2, 3. And on the other hand, by the results of Elfs and Garbert, there exists a conformal branch cover it from M to the half unit sphere, such that the degree of eta is smaller than G plus R. Here G is the genius of M, and R is the number of the boundary component of M. And it 3 equals 0 on boundary M. And we can assume the integration of it I over boundary M equals 0. Here I equals to 1, 2, and 3. And from 9 and Gauss-Bonnet formula, we can imply this strictly inequality 11. And from 10 and Gauss-Bonnet formula, we can imply this equality holds this equality. In particular, if the theta is a right angle, in this case, we have the geodesic curvature Kg equals to a second form of boundary B along E. Therefore, from our assumption, the radial curvature of the ME bar is non-negative. We can imply the following 3 cases. And the last cases happen when the H equals 0 along boundary M, and RE bar minus the radial E bar, the radial E bar equals 0 along M. If theta is not right angle, and we assume the boundary M is embedded, then boundary M separates boundary B by several components, and we choose one of these components denoted by T, such that M intersects T with theta belong to belong to pi over 2 to pi. And we know that the geodesic curvature equals to this function. Then we can take integration. We have this equality, this equation. By Gauss-Bonnet formula for t, because we assume the boundary M is embedded, so we can use the Gauss-Bonnet formula for t. And we have this equation. This equation here is Gauss curvature, and here is total. Here is geodesic curvature. Here is all the number of t. So we have this equation. We have this equation. Know that the all the number of t equals to r or 2 minus r, depending on the choice of t. By the Gauss equation, if the second curvature of amoeba is non-negative, and the second for the form of boundary B is non-negative, and we know that the curvature of t is non-negative. So we have this integration is larger than minus 2 pi r. Here r is the boundary component of M. Now we use 11. We can imply that the following inequality. So the theorem 1, the theorem 2, and the theorem 3 finished. Now we prove the theorem 4. Let's recall the definition of the Merce index. The Merce index of M we denote INDM, which is the maximal dimension of the subspace S of F on which Q restrict F is negative, definite. And here F is denoted in this way. Here is the wetting area preserving, and Q is here. And geometrically, the Merce index is the number of the perturbation directions which strictly decrease area up to the second order. So if the Merce index is 0, that means the hypersurface is stable. Now we look at the eigenvalue problem. For the Jacobi operator J, denoted in this way, with boundary condition. According to the spectral theory for compact linear operators, there exists a non-decreasing and diverging sequence, lambda 1 to lambda k of eigenvalue associated to the L2 of normal basis, phi k of solutions to the eigenvalue problem. 13 equation. By Rayleigh formula, the eigenvalue lambda k has the following variational characterization in this way. And here, the vk minus 1 equals to phi 1 to phi k minus 1. And the v and the orthogonal vk minus 1 denote the orthogonal complement of vk minus 1 with respect to the inner product of L2. Now we give the relationship of Merce index and eigenvalue of 13. Let k be the number of the negative eigenvalues of 13. Then we have this equality. That means the Merce index have the lower bound and the upper bound of about the k. Therefore, we only need to estimate the number of the negative eigenvalue of 13 in order to estimate the index M. Now we give the propositions proof. Let Vk equals to phi I from I to 1 to k be the subspace consisting of the first k eigenfunctions for 13. Since the Q phi I is strictly than 0, smaller than 0 for I equals to 1 to k, and we have the S is subspace in Vk, and the index of M is smaller than k. And on the other hand, we consider a linear operator L Vk to the one-dimensional Euclidean space R, denoted by this way. It follows that the index M equals to the dimension of the kernel of L and equals to the dimension of Vk minus the dimension of the image of L is larger than k minus 1. So the position is holds. And recently, Chuan and Zhou focus our work and show the following precious theorem. Let M in B be a stationary hypersurface of type 2 partitioning, then this type 2 Morse index is equal to k minus 1 if and only if there is a smooth function u such that this equation holds. Otherwise, it is equal to k. This theorem is very beautiful results. Now we give our proof of theorem 4, and the argument is following the argument of Savo, Amber, Carlotto, and Bishop. By using the coordinate of harmonic one form, and we can prove the following lower bound for the Morse index. Given a vector field psi on the sphere M2, and we denote psi power b by its D1 form. The H1T M boundary M denoted in this way. Light psi from 1T to R power dk in this way. And here, the UI denotes the product of psi EI and Q range from 1 to k, and I smaller than J range from 1 to D. And we observe that psi is a linear operator, and H1T M boundary M over kernel phi equals to image phi, and the phi is a subspace of the R power dk. And because M is surface is surface, so the dimension of M is 2. So we have the H1T equals to the first homology group H1 and boundary MR. Thus, we have this equality. Now we claim the definition of kernel phi equals 0. That means the kernel phi equals 0. We use the argument of contradiction. We take the psi b, psi power b is not 0. It belongs to kernel phi. That means the UI belongs to the orthogonal complement of Vk. Thus, Q UI is larger than 0 for any I from 1 to D by the variational characterization of the eigenvalue problem 13. So from this equality, we can apply the left-hand side inequality. And by our acceptance of theorem 4, we have the right-hand side strictly inequality. So we get a contradiction. That means the phi has a trivial kernel. That means the claim holds. That means this is 0. So the K has a lower bound. So the merge index has a lower bound. Now we give the theorem 5's proof. Here is a higher dimensional case, and define the H1N in this way, and the UIG in this way. Here, mu is a unit normal vector field of X from M to B, and we assume the number of the negative eigenvalue of 13 is K. Light phi from H1N to the ordinate space in this way. Here, the UIG functional define V psi by 21, and Q range from 1 to K, and J smaller than J range from 1 to D. And we observe that phi is a linear operator and have this equation holds, and the emission of psi is subspace of R power the D and the opening space. So we have this equality, this equality, this equality, and by the ACS theorem 3, we have the following isomorphism. The H1N M boundary M equals to the first homology group H1 M boundary M R, and record the half proposition that the merge index of M is larger than K minus 1. So the next we only we claim that this is vanish. That means this is 0. So K has the lower bound, and this lower bound is this the dimension of the first homology group. And we use the contradiction, the argument of contradiction. For any cosine B is non-zero, one form is belong to a kernel phi. That means the UIG belong to the orthogonal complement of VK. Thus, we have the Q UIG is larger than 0 by a variational characterization of the eigenvalue problem 13. And from our exception, we have the right-hand side strictly inequality, and this equality can imply the left-hand side inequality. So we get a contradiction. That means the claim is true. So the theorem file is finished. Thank you for your attention. Thank you very much.